We'll take a short break from vectors and talk about constants in Verilog, in particular integer constants. Integers can be specified using either decimal, hexadecimal, octal, or binary formats. And there are two ways in which we can express integer constants. The first way is a very simple way in which we just use a decimal number. So for example, if we take the number 12, in Verilog this represents the decimal value 12. And to specify a decimal, we use digits 0 through 9, and we can represent both positive and negative values. The second way in which we can specify an integer constant is to use the following format. It consists of a number of parts. The first part, which is optional, is a size value. And this is an integer indicating the number of bits that will be used for the constant. Following that, we've got the apostrophe character. And after that, we've got a base. Now the base can be one of these four bases. We can have a binary, octal, hexadecimal, or decimal base. And to represent a binary base, we use the lowercase b or uppercase b. Octal is rarely ever used, so we don't need to worry too much about that. Hex uses lowercase h or uppercase h, and decimal d, lowercase or uppercase. And that deals with the base. And following the base, we then have the actual number. And the number is specified using the digits for a given base. So for example, if the base is binary, we can only use the digits 0 or 1. If the base is hex, we can use any one of the 16 hexadecimal digits. And if the base is decimal, we can use any one of the 10 decimal digits, so 0 through 9. In addition, it's also allowable to use the underscore character when specifying the number, as this can make it more readable, particularly dealing with binary values. So some examples are shown here. Let's take the first one. We've got the integer 7, which indicates that we have 7 bits for our constant. We've got the apostrophe character. We then have the base, which is b. So following the apostrophe, we've got b. And then following that, we've got the actual number. And because we've used b, the number must be in binary. And in this example, it's 0, 1, 0, 1, 1, 1, 0. So we've got a total of 7 bits. And that's the size that we've used here. So this column gives some examples using this format. And this column just gives the value in binary. The second example here, we've got 7 bits in binary. And this time we use an underscore to make it more readable. So you can group bits into 4, 8, whatever number of groups you want. And by using an underscore, it just makes it more readable. And you can see we have the same binary value as we had for the first example. The next example indicates that we have a 5-bit constant. We're using a binary representation. And this time we only specify 2 bits. So it's a 5-bit constant. And what happens is that the 2 bits we specify are the lower 2 bits, and the remaining bits are filled with 0. So this is the actual 5-bit value that results from this code. Another example here, we've just 2 bits given, but it's a 5-bit value. And even though both bits are 1, remaining bits are filled with zeros. The next example, we've got an 8-bit value, and this time we're using a hexadecimal representation. The digits that follow H are hexadecimal digits, in this case 3A, and the equivalent binary value, you can see for 3 it's 0011, and for A it's 1010. Here's an octal example, rarely ever used. And this example here is for the case of just using a decimal value without any size. And in the case where no size is given, for our system, it defaults to a 32-bit value. So when you omit the size, we have a 32-bit value. Another example of an unsized constant is the following: apostrophe B011. So this says it's a binary value, and because we've omitted the size value, this is actually a 32-bit binary value. So it's equivalent to 000 the whole way down to 011, and we have a total of 32 bits. When dealing with binary, we can use the values 0, 1, but we can also use X and Z. Take the first one, we've got a 6-bit number in binary, and we've only listed 4 bits, so 010X. And because the most significant bit of the 4 is an X, the remaining 2 bits are filled with X's. And the same happens with Z. So what happens anytime you provide less than the number of bits? If the most significant bit is an X, then the remaining bits are an X. And if the most significant bit is Z, the remaining bits are filled with Z. And that's the last point we make here. If the value provided is smaller than the number of bits, then the value is extended as follows. In the case of the most significant bit being a 0 or 1, we fill it with zeros. We saw that in these examples here. And in the case of X and Z, it's extended with X's for an X in the most significant bit position, or Z if Z is in the most significant bit position. There are some additional details with constants when we talk about signed and unsigned quantities. All the examples we've provided here are all examples of unsigned constants. So all these numbers are treated as unsigned. Later on, we'll go into the detail of what the difference between signed and unsigned is. But for the moment, this provides us with a way in which we can represent constants of a given size in Verilog. And we leave this slide with the following question. Why do computer and electronic engineers get Halloween and Christmas mixed up? Because the 31st of October is the same as the 25th of December. Okay, let's get back to vectors and look at another way in which vectors can be used. On this slide, we look at bus concatenation. And this is a very useful way for grouping bits together to form vectors. And the main idea is the use of curly brackets, which provide us with the bus concatenation operator. And what happens is that using curly brackets, it's possible to group bits together separated by commas. And the idea is that collectively this creates a larger group of bits. So let's look at the example we've got here. We've got our usual declaration, an 8-bit vector of type reg, databus, and a 4-bit vector of type wire, control. And we want to update certain bits of the databus. Now to see what's happening, let's take the right hand side first of all. What we've got here are 3 groups of bits, 1, 2, and 3. So we've got 2 bits here. It's a binary constant with the value 0, 1. We've got a single bit here. It's just a bit from the wire control at bit position 0. And we've got 2 bits here. We've got the control bit at position 1 and 2. So we've got 2 bits, 1 bit, and 2 bits. And in total, this gives us a 5-bit quantity. So we've constructed a 5-bit vector using smaller groups of bits. And you do so by collectively grouping them together, separated by commas, and using the curly brackets to enclose the entire group. And on the left hand side, we've something similar. We've got 2 groups here. This is the first group, and this is the second group. We've just got 1 bit here. We're just accessing bit position 1, or the second bit in databus. And we've got 4 bits here. We go from 7, 6, 5, 4, those bit positions in databus. So you have 4 bits here. So in total, we have 5 bits here also. And if you want, it's sometimes useful to list out all the individual bits, especially when you are getting to grips with this at the start. And that's what I've done here. If you look at the right hand side, I've labeled all of the 5 bits. The least significant bit is the bit at position 1 in control. The next one is the bit at position 2 in control. That takes care of that group of 2. Then you've got the bit at position 0 in control 0. Then you've got the bit 1 and the bit 0. So these are our 5 bits on the right hand side. And on the left hand side, we've got data bus 1. And then we've got the 4 bits in data bus from 7 down to 4. So this is a mistake. This should be 7, 6, then data bus 5 and data bus 4. Then we've got our 5 bits. So what happens with this assignment is that the least significant bit on the right hand side is evaluated and copied into the least significant bit on the left hand side. The next bit is evaluated, whatever on the wire at this bit position is then copied into this, and so on. So there's a one-to-one correspondence in terms of the assignment that occurs. And the main point with bus concatenation is that we group a comma-separated list of expressions using curly brackets. And in our example, this expression is a constant, this is a bit select, and this is a bit part. And we see that we can have more sophisticated expressions when using bus concatenation, with some examples during later segments. Here's another example to just illustrate the use of bus concatenation. If we look at the right hand side of the assignment here, we've got opening curly bracket and closing curly bracket. So we're grouping bits together using bus concatenation. Now in this example, our first group of bits is given by this expression. We've got our comma, and second group of bits by this expression. So the second group is simple, it's just a single bit. If we look at the least significant bit in this group, it's this bit here. So data bus 7 drives the least significant bit of control. Now when you've got a vector name on its own, we're referring to the entire group of bits for that vector. So control represents 4 wires, and the least significant bit of control is this wire here. So what's happening is we're driving the value from this expression, which is just data bus 7, onto that wire. So if you want to look at what that looks like, it's the same as if we connected this bit directly to that wire. Now if we look at this group here, what we've got is data bus 4 down to 2. So we're referring to the bits at bit position 4, 3 and 2. So 4, 3 and 2. Now in this example, you'll note that we take those bits and we combine them with a constant. So the constant is the 3-bit value 0, 1, 1. So what's actually happening here is this expression is evaluated, and the value of that expression drives 3 wires on the control vector. So the least significant bit is ANDed with this bit. So what we effectively have is an AND gate and a 1. The next bit is a 1. So this bit is also ANDed with a 1. And then the last bit here is a 0. So the value at bit position 4 is ANDed with a 0. We make sure to make the connection in the proper order. So the least significant bit of this expression connects to this bit. The way to think about it is that this is the expression that drives those 3 wires. For control 0, the expression is so simple, it's just that the bit directly drives the wire.